Okay, so let me see if I can explain the COVID code without exponential rates, which is a more general model and more realistic. Now, for the COVID code with exponential rates, you should have discrete equations that look like this. Notice that Sj plus 1 depends on Sj. Here you have the reversion term. Here you have the term of people who become infected, and here's the term of people who become vaccinated. All right, so each one of these has rates as transitions, and remember, every positive term has to have a negative term. This positive term that the recovered becomes susceptible comes from the recovered term. So each time you can think of this kind of as fluid moving around. Here you have this fluid that moves from recovered to susceptible. And of course, this here is going to move from susceptible to exposed, and then this here is going to move from susceptible to vaccinated. And so these are equations you should have already. Now, in these equations, the transitions are proportional to the compartment size. All right. In other words, here we have this transition is proportional to the number of recovered. This means that any person in the compartment is equally likely to make a transition regardless of how long they have been there. This is not realistic. For example, let's consider the recovered who revert to susceptible. Currently, we have the term rho n Rn to model this process. But in actual fact, immunity lasts for several months. Right? So what this is saying is that everyone has that you can be newly recovered and immediately become susceptible again. No, that's not true. You're going to be recovered for a while and then gradually revert to susceptible. All right. So the exponential rates model does not accurately capture that. So we're going to make a better model. All right. So this is what we can do. For subclass n, so we have two subclasses. We have n equals 0 and 1. Here, why don't I? Okay, so here let me just make this better. To make a more realistic model, we can do the following. Okay, for subclass n, where here n is going to be 1 and 2, 0 and 1. Okay, all right. All right, so maybe that's going to be clear. Where are we? For subclass, we may define a function, rho n. All right, before rho n was a number, was a coefficient. Now we make rho n to be a function. All right, where here it function from the natural numbers, 0, 1, 2, 3, 4, 5, 6, to this interval, 0 and 1, such that rho n of k is the probability that an individual reverts after k plus 1 days. He's not going to revert initially. So here is he's going to be recovered for at least 1 day. So we have rho n. So reversion starts at 1 day after you've recovered. All right. Now these probabilities need to add to 1. So if we sum over all k, now so you either revert after 1 day, 2 days, 3 days, 4 days, 5 days, etc. At some point you're going to revert. We'll say that sum is equal to 1. In fact, it's possible that you would never revert. So why don't we change that? This is going to be less than or equal to 1, so we can do that. Right. In fact, it is possible that you never revert. All right, now, given the function rho n, so here I'll make this clear. This is rho n of k. All right, so notice that we've changed things a little bit. It used to be a number, now it's a function. So given this function, how do we create a formula for the number of recovered who revert to susceptible at time j plus 1? Now let me be more clear about this. Not at time j plus 1. It's in the time interval, j to j plus 1. All right, so who reverts during that time interval? That's what this update is showing. It's showing, for instance, this term here. This is showing the people who revert between day j and j plus 1 over that 24-hour period. All right, so that's what we want to get. All right. So let's define some notation. So we'll denote by Rn of j. So we're now defining some new variables. Rn. Rn of j are the newly recovered individuals. So these are the people who are just entering the recovered compartment. Okay. So all right. And so we have Rn of j and R out of j. These are the people who are newly revert to susceptible. All right. Okay. So we can write the equation for R this way. The people at day j plus 1, the total number of recovered are the people who were recovered at time j plus the people who came in minus the people who went out. That should be pretty intuitive. All right? All right. So now, according to the definition of rho n of k, we're now looking at rho n of k. So where are we? According to the definition of rho n of k, where are we? Here we are. According to the definition of rho n of k, a fraction rho n of 0 of the population that recovers in this time interval will revert to susceptible in the next time interval. All right? So remember, rho starts at 1. So this proportion, rho n of 0, are the people who come in during this interval and revert during the next interval. Similarly, fraction rho n of 1 of the population that comes 2 intervals previous will revert. Okay? And so on. All right? So you can write this down. Maybe I can draw a picture. And so let's see if we can do this. We'll make our timeline here. And we have times here. Okay, and we'll mark these times. So let's make this time, this is the start of j plus 1. Here's j minus 1, and then j minus 2, etc. All right. All right, now in each time interval, I'm going to have the rho ins and the rho outs. So here, this is going to be rho in of j and rho out of j. Sorry, R in of j and R out of j. Let me make this bigger so I can make it more higher quality drawing. Okay. That's really pretty bad, so let's go ahead and rewrite that. Just rewrite that. One of these days I'll learn how to type, but writing is okay for now. Right. So during this interval I have R in of j and R out of j. At this time I'll have R in of j plus 1, j minus 1 rather, and R out of j minus 1. And let's do one more. And then this one's going to be R in of j minus 2 and R out of j minus 2. Okay. So the question is, how many people revert during this time interval? Okay. Well, some of these people who just came in will revert. So some of these people will revert. How many of these people revert? Well, that's rho of 0. I'm not using the subscript n, but there's going to be a subscript n on everything, right? So this is going to be rho of 0 times R in of j minus 1. Okay. How many of these people revert? Well, they've been there for 2 days. So that's going to be rho of 1 times R in of j minus 2. All right. How many of these people revert? Right. It's going to be the same process. So you're going to be adding up these terms, which is exactly what we have in our spreadsheet. That's exactly what we have here. Where'd it go? Right here. Okay. So here's my sum of terms. And in fact, I should sum over all past time. So I go all the way back to the beginning. And this is my first reverted. Okay. And of course, I can write this using summation notation. Okay. All right. Now, so we have R out. Now, you can see R out depends on R in. So we're going to have to work backwards and consider R in. Okay. Now, where does R in come from? Here, let's fix this. This should be like this. Where does R in come from? Well, remember, R in comes from the infected who recover. All right? So R in is the same as I out. Okay? So I should, instead of saying R in comes from I out, it's going to be R in is the same as I out. Right? It's not just comes from, it's exactly the same. Okay. R in is the same as I out. So we need to consider the expression for I out. But I out is going to be very similar to R out. Okay? In the original discrete model, we had I out of J is equal to gamma n times I n of J. All right, so this where gamma n was a fixed number. Now we're going to have to change this gamma n into a function. Okay? So by similar reasoning, let's see, we should change the vector gamma into a function so that we have, all right, that's what I want to do. I want to change the vector gamma into a function. Now I out is going to be a sum over all past times of my gamma function times my infected in each time interval. All right? And then R out, remember R in is a number and I out is a vector. So here we just need to sum the components of I out. I can write that this way as a dot product with I out and the vector 1, the vector of all ones. I see I'm missing a little bit of a parenthesis here, so let me fix that. All right. Okay, so now we have I out. Okay. So we may obtain similar expressions for E out and I in. So that'll leave it for you. We'll be able to express E in terms of outputs from Sn. So now that's I out and E out and I in. Now to get E in, that's a little bit more complicated. So let's see. So I'll make this a new paragraph. So E in is a little bit more complicated. Okay. Okay. We will be able to express E in terms of outputs from Sn and Vnk. So you know that people get exposed from the susceptible and the vaccinated compartments. And we must be careful here because these three compartments have two outputs. Some people who are vaccinated once will get vaccinated twice. Some people will get infected, right? So we have two outputs. So we'll express these two outputs as out I and out V. Okay, so these three compartments are going to have two different outputs. We're going to have separate equations for those two different outputs. Now, the out V equations are very similar to what we have up here, so I'm not going to talk about those. The out I's are a little bit more difficult. They need special attention because they depend on Ij as well as previous outputs. All right, so you might wonder why Ij. So the reason Ij is that people who are infected in the time interval j to j plus 1 depend on how many people infected are running around. Not on people who were infected in the past, not on how long they were infected, but it just depends on how many people are infected during this time interval. So that's why we have I of j here. We don't have any sum over I. You're just looking at the current infected population. Okay? But we do have a sum over the past s's because however long you've been susceptible, may influence your infectivity. Okay? And this is the same for the vaccinated classes. The vaccination is going to fade. So your infectability is going to depend on how long you've been vaccinated. All right, so we're going to have these sums here. All right. So we're going to have to define all of these rates as functions instead of as numbers. And we'll see how to do that below. So here's your assignment. We've defined these out variables. We've also defined in variables, but the in variables are always equal to corresponding out variables. So we can just look at the out variables. So what you need to do is rewrite equations for all of these out variables. And we'll write the equations for j. I've already written a couple for you, right? I've written the equation for s out. Now, this one here, s in, you can replace this with with r out, right? Because s in is the same as r out. Okay, so you shouldn't have any invariables in your equations. Okay. And then let's see. Let me just. I'll make a note here. Okay, so I'll just say that's a note that your equations should not have any invariables because these are all equal to corresponding out variables. Okay, so you don't need any invariables in your equations because you can replace it with an out variable. All right, so rewrite your equations like this. Do it in LaTeX. You can put it in a markdown. Okay, now for number 2, I want to emphasize this because this is important. I think that this will give me bold. Okay, so make a copy of your code. All right, I want to make that bold. So I think what I need to do here is I go 2 stars. Let's see if that helps. You don't want to lose your previous code. So here, when I say make a copy of your code, what I mean is your exponential code. Make a copy of your exponential code. Okay, so I want to compare the 2 codes. All right. All right. Now, you also will need to write functions for all the transition rates. For the moment, we can assume that these transition rates are exponential. So in fact, the new model should agree with the old one if you do everything right. So for example, for the reversion function, instead of calling it rho, we'll call it rho fun. And in fact, rho fun will just be rho because it won't depend on the length of the history. All right. So that will be our initial specification. All right, number 4. So this is the big one. Use your functions to rewrite the code according to the new equations. All right, so you'll have to use these, you'll have to define these functions, you'll have to implement all of these equations. So you can implement them in this order, right? And then the thing is that the complicated equations will be the out equations. These equations will be quite easy because, for instance, Snj plus 1 is just the invariable, which would be it would be Sn of j plus the invariable, which is going to be Rn out, and then it's going to be minus Sn out. All right, so these equations, Snj plus 1, etc., these will be very easy. The complicated equations will be the equations above. All right, but you can simply rewrite those equations in your time loop. Now, for the initializations, the out variables will be the same as the original variables. Remember, you had to give initial values for the original variables. So instead of calling it S out like that, well, maybe it'd be a little bit more clear if I say S out with an underscore. So to do that, you have to do this. Whoops, no you don't. You just have to do this. Okay. All right. Notice how if I wanted to include code in my markdown cell, notice how I did that. I put these forward quotes there. That's a handy thing to know. Okay, you may want to use that. Okay, now at the bottom of your code, after the time loop completes, you want to add 2 plots that will show all the compartments as a function of time. Now you'll make one plot for each subpopulation, the high risk and the low risk, and of course the high risk and the low risk both have alpha and delta variants, and you will need to include those separately. So the En is actually going to be 2 lines, the In is going to be 2 lines. Okay. Okay. So let me just note that. So note that the vector compartments P and In will be represented as 2 separate graphs. Okay? All right, so I hope that's clear, and we'll work on that. This is going to take a while. Please feel free to consult with me. This should be fun, and we should have something good come out of this. All right, thanks. Bye.